Erwin Schrödinger entered the world with a unique perspective, a kind of double vision that would stay with him throughout his life. Born in Vienna on August 12, 1887, he was raised in a city where music and mathematics were seen as closely related disciplines. Turn-of-the-century Vienna was a hub of culture, characterized by both vibrancy and underlying unease, a city that projected imperial confidence while harboring deep uncertainties. Schrödinger inherited this tension early on, not from political climate, but from his own home environment. His father, Rudolf, owned a small linoleum factory and possessed a quiet but profound love for science. He taught young Erwin to observe nature meticulously and to describe it with disciplined imagination. His mother, Georgine, came from an academic background and infused their home with literature and languages. Erwin learned to read in multiple languages and to think in diverse modes. He found joy in geometry and poetry, and he was equally comfortable with complex calculations and evocative metaphors. Later in life, people would remark that Schrödinger didn't just perform physics. He seemed to feel it, much like a composer intuitively grasps a musical theme before developing it into a full score. His formal education only amplified these tendencies. He excelled in mathematics and physics, but also showed a keen interest in philosophy. He didn't view knowledge as a collection of isolated compartments. Instead, he saw it as a unified structure where different fields were interconnected and accessible to one another. When he entered the University of Vienna in 1906, he was immediately drawn to theoretical physics, especially under the guidance of his teacher, Franz Exner. By the time he earned his doctorate in 1910, he had already internalized the two major influences that would shape his career, Maxwell's electrodynamics and Boltzmann's statistical mechanics. To Schrödinger, the world appeared as a system of invisible waves and hidden probabilities, long before quantum theory explicitly called for such a viewpoint. Then history intervened. World War I erupted, shattering Europe, and Schrödinger, like many young Austrian men, was drafted into the army. He primarily served in artillery units, often stationed near the Italian front. The war did not instill nationalism in him. Rather, it intensified his sense of isolation. He was not suited for the demands of military life, the marching and shouting. His nature was to contemplate and analyze, and the war years were lean, cold years of waiting for the world to heal so that intellectual pursuits could resume. In the aftermath of the war, Europe was exhausted and yearning for fresh ideas. Schrödinger returned to academia, progressing through a series of positions in Jena, Stuttgart, Breslau, and eventually Zurich. These were not glamorous appointments, but rather the steady ascent of a talented theorist in a continent marked by both declining empires and growing intellectual aspirations. In Zurich in 1921, he found what he needed for his next major breakthrough: stability, supportive colleagues, and location far enough from the lingering shadows of Vienna to allow him to reinvent himself. His personal life was complicated. Schrödinger was married to Annie Bertel, a woman who understood him deeply, but couldn't entirely contain his restless spirit. He was affectionate, but also prone to seeking connections beyond the confines of his marriage. He seemed to believe that love was a vast, open landscape, not confined, fenced garden. This led to complex and sometimes problematic relationships outside his marriage that were never fully concealed and never neatly resolved. While it's easy to pass judgment, it's more accurate to see this as an aspect of his overall temperament. The same inclination that resisted compartmentalizing ideas also resisted confining his heart to a single path. Though it may sound romantic, it wasn't always compassionate, but it was undeniably Schrödinger. By the mid-1920s, a storm was brewing in the world of physics. The established classical model, particles as miniature billiard balls, light as a continuous wave, was beginning to crumble. Atoms behaved in unexpected ways. Spectra displayed strange patterns, and the concept of quantization had infiltrated science like a disruptive seed. In 1925, Werner Heisenberg proposed matrix mechanics, a new mathematical framework that treated physical quantities as non-commuting matrices. The theory was remarkably effective, but it felt foreign, almost mechanical, to many physicists. Schrödinger read Heisenberg's paper and was impressed, but also felt a sense of unease. The approach seemed akin to describing a symphony using a spreadsheet. He saw an alternative, something more continuous, something closer to the wave-based ideas that had been lingering in physics since de Broglie suggested the possibility of particles possessing wavelengths. Schrödinger was uniquely positioned to embrace this possibility. He had immersed himself in wave theory for years. Maxwell's equations and the language of vibrations were already second nature to him. In late 1925 and early 1926, while on a secluded retreat in Arosa and later back in Zurich, Schrödinger embarked on a quest for a new equation. The story of those months has become a legendary tale in physics. He worked with intense focus, sometimes writing in extended sessions that felt almost trance-like. He was also in a heightened emotional state. Letters and diaries suggest he was involved in a passion affair, and a combination of exhilaration and secrecy served as a unique catalyst. Schrödinger's most profound insights often emerged when he was in a state of heightened awareness, blending thought and feeling. The result of his efforts, in January 1926, was a wave equation that now bears his name. It depicted the electron not as a point particle orbiting a nucleus, but as a wave whose shape evolved smoothly over time. The equation was remarkably simple, elegant, and powerful. In one fell swoop, it explained the energy levels of the hydrogen atom and accurately predicted spectral lines. The erratic, unpredictable atom of the old quantum theory was suddenly transformed into a stable, standing wave. Matter didn't merely possess waves. Matter itself was wave-like, at least at its most fundamental level. Schrödinger's wave mechanics spread rapidly across Europe. It provided physicists with a visual and mathematical tool that they could intuitively grasp. While Heisenberg's matrices felt abstract, Schrödinger's waves seemed almost tangible. It was as though a fog had lifted, and the atom had regained its form. However, the fog hadn't completely dissipated. Amidst the excitement, a deeper question arose. What exactly is a wave? Is it a genuine physical ripple in space? Or is it a mathematical construct representing probability? Initially, Schrödinger hoped that the wave was real, a literal distribution of matter or charge. He wanted to preserve something akin to the classical worldview, albeit in a more refined form. But soon, Max Born proposed that the wave function didn't describe material density. Instead, it described the probability of finding a particle in a specific location. The square of the wave's amplitude represented this probability. Schrödinger initially resisted this interpretation. To him, probability felt like a concession to ignorance rather than a fundamental law. Yet, the evidence and the internal consistency of the emerging quantum world pushed everyone, including Schrödinger, toward Born's interpretation. Simultaneously, the rivalry between wave mechanics and matrix mechanics intensified. Which theory truly represented quantum reality? Schrödinger and Heisenberg possessed different temperaments and different perspectives. The community seemed headed for a clash. However, within a few months, it became clear, largely through the work of Dirac and others, that the two theories were mathematically equivalent. They were not opposing forces, but rather two different languages describing the same underlying reality. Schrödinger had not overturned Heisenberg. He had completed the picture. For this, he became one of the most celebrated physicists of his time. Yet, this recognition did not resolve the internal philosophical conflict within him. He had played a key role in developing quantum mechanics, but he was deeply uneasy with its implications for our understanding of reality. Waves transforming into probabilities. Particles existing in multiple states until measured. Nature resisting definitive characterization without the intervention of an observer. Schrödinger, being a realist and a lover of continuity, could not accept this without a sense of profound unease. This unease would later inspire his most famous thought experiment. But for now, in 1926 to 1927, he stood at the pinnacle of discovery, an Austrian theorist whose wave equation had become the very heartbeat of modern physics, even as his own heart remained conflicted about the meaning of that physics. Part 1 concludes with Schrödinger in Zurich newly famous, having channeled his double vision into one of the most beautiful equations of the century. The next part will explore the immediate aftermath, his debates with the Copenhagen School, his move to Berlin, and the gradual emergence of his resistance to the deeper implications of the quantum world, a resistance that would ultimately manifest as a cat in a box. The success of wave mechanics should have been the moment Schrödinger settled into triumph. Instead, it became the moment he began to drift away from his own creation. In early 1926, his equation was everywhere, solving the hydrogen atom, illuminating spectra, giving the atom a comprehensible form once again. Colleagues wrote to him as if he had rescued physics from the brink of disaster. Yet, the more his wave function permeated the field, the more Schrödinger felt a quiet unease growing within him. He had introduced a new language for describing nature, but he disliked the meaning that language was beginning to convey. Initially, Schrödinger envisioned his wave as something tangible, a smooth distribution of charge or matter, a real wave propagating through space. The visual reassurance of this idea was important to him. Without it, the world felt too ethereal. But Max Born's probabilistic interpretation arrived like a chilling gust of wind. Born argued that the wave function was not physical at all. It was merely a tool for predicting the outcomes of measurements. The wave didn't tell you the precise location of a particle. It told you the probability of finding it there. Experiments seemed to support Born's view, and the mathematical framework cohered around it. Everyone else began to agree, but Schrödinger remained unconvinced. He wasn't rejecting the mathematics. He was resisting the philosophical implications. To him, probability felt like an admission of ignorance masquerading as a fundamental law. He desired a reality that was continuous and objective, not contingent on the measurements performed by observers. When he encountered the emerging Copenhagen interpretation, Bohr and Heisenberg's assertion that quantum theory described knowledge, not the intrinsic nature of things, he felt as though the very foundation of physics was being quietly undermined. It was one thing to acknowledge that nature was subtle and complex, but quite another to accept that nature was somehow incomplete or undefined until it was observed. Still, he was too intellectually honest to simply dismiss these ideas. Schrödinger engaged in debates through papers and letters, searching for an interpretation that preserved the reality of waves. He explored whether the wave function could represent a smeared-out electron rather than a cloud of probabilities. But each time, the empirical evidence contradicted his views. Quantum jumps, interference patterns, scattering data, all pointed toward the strange new perspective. So, Schrödinger shifted his approach to debate rather than outright rejection. In 1927, he attended the famous Solvay conference in Brussels, where the quantum revolution confronted itself in a single room. Einstein was present, skeptical like Schrödinger, although his skepticism was rooted in an older, more established worldview. Bohr and Heisenberg were there, defending probability and complementarity with unwavering intensity. Dirac, Pauli, de Broglie, Curie. Virtually every major figure in physics was in attendance. The conference became a kind of trial for the very nature of reality. Schrödinger presented wave mechanics as elegantly as possible, but he also argued vehemently for a realist interpretation. He contended that a physical wave picture avoided the unsettling concept of the wave function collapsing. Bohr countered that the demand for a continuous, visually intuitive reality was a classical reflex, not an inherent necessity. Heisenberg insisted that uncertainty was not a limitation of our instruments, but a fundamental property of nature itself. Schrödinger listened, debated, and departed Brussels with a deeper admiration for his colleagues, but also with increased doubt about their conclusions. He later wrote that Bohr's logic was so tightly constructed that it was difficult to find any flaws. But still, he could not bring himself to accept living within its confines. The disagreement was not about the equations themselves. It was about the kind of universe those equations were permitted to describe. Soon after, his career took a dramatic turn. In 1927, Max Planck invited him to join the University of Berlin as a successor. At that time, Berlin was a leading center for physics, home to Einstein, Planck, von Laue, and a vibrant ecosystem of brilliant younger researchers. For Schrödinger, it was an opportunity to perform on one of Europe's most prestigious stages. He accepted the offer. Berlin was both stimulating and oppressive. The intellectual atmosphere was electric, but the political climate was beginning to darken. Nevertheless, in the late 1920s, science still seemed like a republic above politics. Schrödinger taught refined wave mechanics and conducted research on quantum statistics. He contributed to what we now call Bose-Einstein condensation through his studies on ideal gases, and he explored how entanglement and measurement reshaped the meaning of thermodynamics. His work remained inventive, reflecting the wandering nature of his mind, never content with single, narrow focus. But while Berlin celebrated him, Schrödinger's internal conflict deepened. He observed quantum mechanics solidifying into orthodoxy, and he feared that this orthodoxy represented a metaphysical surrender, a willingness to simply accept that's just how it is rather than seeking a deeper underlying mechanism. He admired the theory's accuracy, yet he couldn't shake the feeling that it provided an incomplete account of reality. Then, history shattered the illusion of safety in the world of science. In 1933, the Nazis seized power. Jewish scholars were expelled, universities were purged, and the atmosphere became poisonous. Berlin, once a beacon of intellect, transformed into a place where minds were hunted. Schrödinger was not Jewish, but he was deeply anti-authoritarian and instinctively repelled by ideological brutality. He also had close Jewish colleagues and friends. The transformation of Germany horrified him. As the Nazi regime demanded oaths and obedience, the university's brilliance felt like a facade concealing decay. Schrödinger left Berlin that same year. His departure was both a moral and a personal decision. He didn't make grand pronouncements or join a political movement. He simply walked away from a country whose spirit had turned against the very openness that science required. He briefly returned to Austria, then accepted a position at Oxford. Exile once again became a part of physicists' life. Europe's best minds were scattering like seeds before fire. Oxford offered safety, but not necessarily comfort. Schrödinger was now a prominent figure navigating a foreign academic culture, carrying not only Nobel-level prestige, but also a reputation for a philosophical stubbornness and a personal life that didn't easily conform to English norms. He was restless, disliked administrative duties, and felt that Oxford's physics environment was less stimulating than Berlin's had been. He published extensively, but his spirit seemed to hover above his work, discontented. In 1935, that discontent took on a strange and vivid form. Schrödinger wrote a paper on what he called entanglement, introducing the word verschränking to describe quantum systems whose states cannot be separated, regardless of the distance separating them. In the same year, he introduced a thought experiment designed to expose the absurdity he perceived at the heart of the Copenhagen interpretation. Imagine a cat sealed inside a box. Inside the box is a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. According to quantum mechanics, before we open the box, the atom exists in a superposition of decayed and not decayed states. If we take the Copenhagen view seriously, Schrödinger argued, then the entire chain, counter, poison, cat, must also exist in a superposition. The cat is simultaneously alive and dead until observed. The absurdity was precisely the point. Schrödinger didn't create the cat to be endearing. He created it to expose the perceived flaws of the interpretation he opposed. He wanted to demonstrate that if quantum uncertainty applied universally, then the macroscopic world would become an impossible blur. Measurement would not simply reveal reality. It would create it. Schrödinger found this idea intolerable. The cat became famous because it dramatized the concerns that many people were quietly harboring. But Schrödinger's goal wasn't merely to gain public recognition. It was to exert intellectual pressure. He was urging his colleagues to acknowledge that something was missing from the narrative. Either the wave function didn't describe everything, or there had to be a deeper mechanism explaining why we observe a single outcome instead of a superposition of all possible outcomes. His argument didn't overturn the Copenhagen interpretation. If anything, it strengthened the resolve of its defenders, but it planted a persistent question in the foundations of quantum mechanics. The cat would haunt physics for the next century, becoming a symbol of quantum weirdness, even though it originated from Schrödinger's resistance to that very weirdness. Part 2 ends with him in exile once more, now in Britain, grappling with the central paradox of his life. He helped build quantum mechanics, and he also became one of its most articulate critics. He has transitioned from a triumphant equation to philosophical rebellion, from Berlin's glory to Europe's crumbling moral landscape. The next part will trace his experiences during the war years, his efforts to rebuild his work in Ireland, and his later attempt to reconcile mind, wave, and reality in a world that had irreversibly embraced quantum mechanics. Exile has a way of distilling life down to its essentials. For Erwin Schrödinger, the mid-1930s represented precisely such a moment, a period when he was compelled to decide what belonged to his intellect, what belonged to history, and what he could no longer realistically consider stable. He had left Berlin because the atmosphere itself had become hostile to freedom. He was now in Oxford, far removed from his former intellectual hub, and yet the intellectual pressure within him had not diminished. If anything, it intensified, because he was now less preoccupied with prestige and more consumed by the search for meaning. Oxford never truly felt like home. The university was respectable and secure, but Schrödinger missed a vibrant European network he had been a part of for a decade. He missed the intellectual sparring with giants. He also missed a certain level of philosophical audacity. British academic culture, in his view, felt cautious and compartmentalized, while his own thinking defied boundaries. He taught, wrote, and attended meetings, but he moved through Oxford like a guest who couldn't quite recall why he had come to the party in the first place. In 1936, after only a brief stay, he left again, this time returning to Graz in Austria. For a time, it seemed like a quiet recovery. He had a professorship, students, and proximity to the mountains he loved. But history was already hurtling toward another precipice. By 1938, the Anschluss incorporated Austria into Nazi Germany. The political darkness he had fled returned to his doorstep. Schrödinger was quickly labeled politically unreliable and dismissed from his position. The sense of déjà vu was brutal. Europe was not just disrupting intellectual life. It was repeating the disruption. Once more, he had to relocate. He accepted an invitation from Eamon de Valera, the Irish statesman who had founded the Dublin Institute for Advanced Studies, hoping to create a sanctuary for intellectual pursuits in a world of turmoil. Schrödinger arrived in Ireland in 1939, just as World War II commenced. Dublin remained neutral, more peaceful than the continents engulfed in flames. In a way, that neutrality suited him. It provided him with distance from the moral suffocation of fascism and from the bureaucratic mobilization of wartime Britain. He could once again think with clarity and space around his thoughts. The institute was young and small. There were no elaborate laboratories, no vast teams, only rooms, blackboards, and books. Schrödinger's presence immediately became the institute's central force. He taught courses not only in quantum mechanics, but also in the philosophical foundations that he felt were being neglected elsewhere. His students, some Irish, some refugees, some international visitors, found him captivating. He could transform a complex derivation into a compelling story, and then transform that story back into a rigorous derivation. His mind moved seamlessly between calculation and reflection, between precise logic and open inquiry. Yet even in Dublin, his relationship with quantum mechanics remained strained. He had helped develop its central formalism, but he still refused to accept the Copenhagen interpretation's assertion that reality was merely a map of measurements. If a wave function described probability, then what described existence? Schrödinger continually returned to this question, like a man circling a locked house. One of his methods of exploration was to investigate alternative ideas. He followed de Broglie's pilot wave theories with interest. He studied how classical limits might emerge from underlying dynamics. He attempted to envision whether collapse could be a physical process rather than an epistemic jump. But none of these avenues fully satisfied him. He sensed that quantum mechanics was a correct theory with an incomplete narrative, like a book whose plot works, but whose narrator is unreliable. The war years also steered Schrödinger toward broader scientific and philosophical domains. In Dublin, he began lecturing on topics that extended beyond the strict confines of quantum theory. Thermodynamics, statistical mechanics, the nature of life, the arrow of time. These were not deviations from his core interests. They were his attempt to determine whether quantum foundations could be better understood by situating them within a larger perspective on nature. This led to one of the most unexpected chapters in his life. In 1943, during a series of public lectures at Trinity College, he posed a question that no one in Vienna or Zurich would have anticipated him asking. What is life? Not in a poetic sense, but in a physical one. How does living matter maintain order in a universe tending toward disorder? His answer was bold and remarkably influential. He argued that organisms feed on negative entropy. They extract order from their environment to maintain their own structure. He also suggested that hereditary information must be stored in an aperiodic crystal, a stable molecular structure capable of encoding complex instructions. These ideas didn't provide a complete solution to the puzzle of biology, but they ignited a spark. When Schrödinger published the lectures in 1944 as the book What is Life, young scientists across Europe and America viewed it as a call to action. Some of the future founders of molecular biology, figures like James Watson and Francis Crick, later credited the book with inspiring them to pursue genetics. Schrödinger, who had never held a pen in his life, had pointed the way to DNA through pure thought. The irony was subtly beautiful. A man uneasy with quantum probability had still planted seeds in a field that would soon rely on probabilities as much as on chemistry. But for Schrödinger, biology was yet another doorway into the question he never abandoned. How can order and meaning arise in a world governed by wave functions and chance? In the late 1940s and 1950s, he continued this interdisciplinary exploration. He wrote on the philosophy of science, on the relationship between mind and matter, and on Eastern thought, particularly Vedanta. He was captivated by the idea that separateness might be an illusion, an intuition that resonated, perhaps reluctantly, with the concept of quantum entanglement. He didn't become a mystic. He remained a physicist, but he allowed philosophy to be a companion at the chalkboard, not just a visitor confined to the periphery of the lab. His personal life in Dublin remained as complex as ever. His marriage with Annie endured through a form of mutual acceptance, and his relationship with Hilda March, a younger woman who lived with him, continued openly. From a modern perspective, this arrangement may seem unstable. For Schrödinger, it simply reflected the way his emotional world was structured. He couldn't live a life of singularity. As with his science, he sometimes caused pain while pursuing a form of wholeness that he could never quite define. Meanwhile, quantum mechanics itself grew stronger. The post-war generation transformed quantum electrodynamics into a predictive masterpiece. Laboratories confirmed theoretical predictions with astonishing precision. Schrödinger admired these achievements from a distance. Yet, he remained uneasy about the foundational narrative. To him, success in calculation didn't eliminate the conceptual ambiguity. It simply made it more difficult to address because everyone felt so confident in the theory's success. In Dublin seminars, he would still gently probe the weak points. What is measurement? What makes one outcome real? Why do macroscopic objects appear definite when microscopic systems do not? He didn't express gloom or pessimism. He posed these questions with a certain weary tenderness, as if he still hoped that a friend would offer him the key to a door he had been staring at for 2 decades. By the late 1950s, with Europe recovering and the New World Order solidifying, Schrödinger began to consider returning home. Ireland had been generous, but it had never truly become a part of his cultural identity. He missed the German language, missed the density of continental intellectual life. He was also growing older, and the repeated moves had taken their toll. In 1956, he accepted a prestigious position back in Vienna. Returning felt like completing a circle. Back to the city of his birth, now older and transformed, yet still carrying the music and logic that had shaped him. In Vienna, he continued lecturing and writing, now regarded less. As time passed, Schrödinger transitioned from a controversial rebel to more of an elder statesman in the physics world. The world's perception of him softened, though his relentless pursuit of fundamental questions remained unchanged. Part 3 culminates with Schrödinger's return to Vienna after the war, achieving fame on 2 distinct fronts: as the originator of wave mechanics, and as a philosophical critic unafraid to challenge the easy acceptance of the theory's implications. He had weathered exile, witnessed the rise and fall of Europe, and unexpectedly influenced the field of biology with a single, impactful book. Yet, the perplexing quantum cat metaphor continued to occupy his thoughts, representing a theory he simultaneously cherished and questioned. The subsequent part will delve into his later reflections, his final intellectual battles surrounding interpretation, and the enduring inseparability of his legacy from the very quantum weirdness he sought to understand. Vienna in the late 1950s was vastly different from the city Schrödinger had left behind as a young man. The empire had vanished, the once bustling cafes were quieter, and the city carried the subtle weariness of surviving 2 world wars and a moral crisis. However, for Schrödinger, returning in 1956 felt less like nostalgia and more like re-entering his formative atmosphere, a world of music, logic, memory, and mathematics, all breathing the same intellectual air. He returned not to recapture his youth, but to live out his final chapter in a familiar, native intellectual language. The University of Vienna welcomed him back as a celebrated, albeit prodigal, elder. He had already become a legend, a Nobel laureate, the father of wave mechanics, and the author of the infamous cat paradox that had permeated culture far beyond the confines of physics. But Schrödinger did not return merely for ceremonial purposes. He came home to continue his persistent questioning of fundamental principles. He taught, he wrote, and he engaged in debates about the foundations of quantum mechanics with the same quiet intensity that had characterized his time in Zurich and Berlin. By this point, the Copenhagen interpretation had firmly established itself in most laboratories. Budding physicists were taught to prioritize calculations and postpone interpretation, if it was considered at all. For them, quantum mechanics was primarily a practical tool that yielded results. For Schrödinger, it was a tool that worked effectively, but still left the core mysteries unsolved. The more successful quantum theory became, the more isolated his discomfort seemed. Yet, he saw this isolation not as a defeat, but as a sign of unfinished work. His later writings increasingly explored the intersection of physics and philosophy. Schrödinger believed that the foundational crisis in quantum mechanics was not merely a technical issue, but touched on fundamental questions about what it means for humans to perceive something as real. In lectures that later formed the basis of books like Nature and the Greeks in Science and Humanism, he traced a lineage from the clarity of ancient Greek thought to the ambiguity of modern quantum physics. The Greeks, he argued, trusted reason to uncover a coherent cosmos. Modern physics had rediscovered coherence in equations, but had begun to question coherence in existence itself. Schrödinger sought to bridge that divide. He was particularly concerned with the role of the observer. The Copenhagen interpretation insisted that measurement was not a passive act, but an integral part of the phenomenon being observed. Schrödinger accepted the formal necessity of this claim, but not its metaphysical implications. He resisted the idea that reality was contingent on human observation, preferring to believe that inquiry should reveal reality, not construct it. In the late 1950s, he frequently returned to the concept of entanglement, a term he himself coined, seeing it as a crucial clue that quantum mechanics was pointing towards a deeper, more fundamental layer of reality. To him, entanglement was not an invitation to abandon realism, but an opportunity to refine realism into something more nuanced and interconnected. This line of thinking led him to explore ideas about the unity of consciousness, which made some physicists uneasy. Schrödinger took Eastern philosophy seriously, not as a passing fad. He was drawn to Vedanta's notion that separateness is a kind of cognitive illusion. If the physical world is fundamentally entangled and inseparable at its core, then perhaps the mind's sense of isolated selves is also not fundamental. He explored this idea delicately in his short book Mind and Matter. He was careful not to claim that quantum mechanics definitively proved mysticism. Instead, he suggested that quantum theory and certain philosophical traditions were converging on a similar intuition, that the world is more unified than our everyday categories typically allow. In seminars, he could still be incisive on matters of physics. He criticized the complacency that treated collapse as a definitive answer. He was skeptical of any interpretation that used the term measurement without clearly defining it. What exactly constitutes a measurement? A detector? A human eye? A neuron? A laboratory? If quantum theory only predicts observations, he argued, then the boundary between the micro and macro worlds becomes vague and arbitrary, a vagueness that offended his desire for clear structures. He believed that a deeper theory would eventually explain how macroscopic definiteness emerges without relying on a special observer postulate. He also watched with mixed emotions as the cat paradox took on a life of its own, straying from its original purpose. In his mind, the cat was a cautionary tale, a reductio ad absurdum, designed to challenge the Copenhagen interpretation. But by the late 1950s and early 60s, the cat was transforming into a mascot of quantum weirdness. Popular science writers embraced it. Philosophers debated its implications. Younger physicists sometimes treated it as an amusing illustration rather than a serious warning. Schrödinger found this slightly ironic, as he had conceived the cat thought experiment to highlight the incompleteness of the interpretation, not to romanticize that incompleteness. Yet, he did not resent the public's fascination with it. Schrödinger was not a man of bitterness. If anything, the cat's fame reassured him that foundational questions still mattered and that people sensed the story was not yet complete. He quietly hoped that new generations, intrigued by the paradox, would push beyond the established habits of calculation. One aspect of his later life that pleased him was the emergence of alternative realist approaches. David Bohm's revival of pilot wave theory in 1952 gave Schrödinger a glimmer of companionship in his dissenting views. Although he did not fully embrace Bohm's perspective, he admired his boldness. It demonstrated that one could maintain a realist interpretation without violating the equations of quantum mechanics. The mere existence of such alternatives implied that the Copenhagen interpretation was not the only viable way to reconcile oneself with quantum mechanics. Schrödinger found solace in this plurality. His personal life in Vienna remained as unconventional as ever. Annie, his wife, remained by his side. Hilda March continued to be a part of his life, and children from these relationships formed his extended family. Viennese society had always been more accepting of complex relationships than English society, and Schrödinger found it easier to live without constant moral judgment in his old city. Nevertheless, this arrangement required gentleness and patience from everyone involved, and those closest to him understood that his emotional landscape, like his intellectual one, transcended narrow boundaries. Despite his advancing age, he maintained a robust correspondence. He wrote to members of Einstein's former circle, to Irish colleagues, and to young theorists who dared to explore questions of interpretation. Visitors described him as physically frail but mentally sharp, with a gaze that could be gentle one moment and piercing the next. He continued his lifelong habit of walking whenever his health permitted, finding that he thought best while moving through the open air. But the effects of aging were undeniable. By 1959, his pace was slowing. The wars and exiles had taken their toll. His notebooks became more reflective, sometimes revisiting familiar themes rather than developing new formalisms. Yet, these reflections were never superficial. They were attempts to chart the moral and conceptual terrain of a theory that had fundamentally transformed civilization. Schrödinger recognized that he had played a role in creating a worldview that would shape not only physics, but also technology and culture in ways he could not fully foresee. He felt a sense of responsibility for its meaning. In 1960, he published a collection of essays that later became My View of the World. While the title suggests a personal perspective, the book reads as an attempt to articulate a deeper sense of human unease. He revisited the question of why the world appears classical to our senses when quantum superpositions underlie everything. He returned to the puzzle of individuality within a fundamentally entangled universe. He entertained the quiet suspicion that the most effective path forward might not involve adding more complexity, but rather discovering a simpler principle that would make the existing machinery seem inevitable. In these pages, one could discern his late-life temperament, less combative in the 1930s, more contemplative, but still steadfast in his refusal to accept ambiguity as the final word. He had not made peace with the Copenhagen interpretation, and he made no pretense of having done so. But he had come to terms with the fact that science sometimes lives with open questions for longer than a single lifetime. By early 1961, his health had deteriorated significantly. He suffered from tuberculosis-like complications and a gradual weakening that made long walks increasingly difficult and lectures less frequent. Even then, friends noted that he would still brighten up when someone posed a genuine question about meaning. He had always lived for those moments. The moments when physics transcended mere calculation and became a way to inquire into the nature of existence itself. He passed away on January 4th, 1961, in Vienna, at the age of 73. The city that had provided him with his initial intellectual nourishment also gave him his final resting place. Hartford concludes here, with Schrödinger back in his homeland, an old man surrounded by both honor and uncertainty. He spent his final years challenging the easy acceptance of quantum mechanics implications, writing in pursuit of a realism that could coexist with entanglement, and witnessing his cat paradox become both a warning and a symbol. The final part will explore what he left behind after his death, how his ideas continue to influence quantum foundations, how the cat re-entered physics through experiments and philosophy, and why Schrödinger became inextricably linked to the very mystery he had attempted to unravel. Schrödinger's death in January 1961 did not mark the end of his story. It initiated a lasting echo. The man who had gifted quantum mechanics with its most elegant equation, and then spent decades grappling with its meaning, left behind a legacy that felt paradoxical in the same way a quantum state feels paradoxical. Clear in calculation, unsettled in interpretation, and impossible to distill into a single classical image. In the years immediately following his death, physics continued its relentless advance along the path that had consistently troubled him. Quantum electrodynamics evolved into a high-precision tool. Particle accelerators grew larger. Experiments became more definitive. The standard model began to emerge, based on quarks and gauge fields, and by the 1970s, quantum theory had become the unquestioned foundation of modern science. To many working physicists, Schrödinger's interpretive anxieties sounded like echoes from a bygone era. The prevailing attitude within the community was straightforward. The math works, so why worry? Yet, the underlying unease did not vanish. It went underground, taking root where Schrödinger had planted it. His cat thought experiment, initially intended as a form of protest, became a kind of guiding light, constantly illuminating the boundary where the microscopic rules of superposition intersect with the macroscopic experience of definite outcomes. Each generation that attempted to ignore foundational questions found the cat lurking at the edge of its confidence. If quantum superpositions are indeed real, then why do we observe cats in a state of being both alive and dead? What precisely qualifies as a measurement? Why does the wave function invariably collapse into a single definite outcome? Schrödinger had not provided definitive answers to these questions, but by emphasizing their importance, he had made them impossible to ignore. During the 1960s and 70s, philosophers of science adopted the cat as a central case study. More significantly, physicists gradually returned to it, not out of nostalgia but out of necessity. John Bell's theorem in 1964, though not directly connected to Schrödinger's work, picked up the thread of entanglement that he had highlighted and demonstrated that quantum non-locality was not merely a philosophical abstraction. It was a real phenomenon that the universe had to accommodate if quantum predictions were accurate. Bell's inequalities transformed entanglement from a conceptual curiosity into a testable frontier. Experiments conducted throughout the 1970s and 80s repeatedly violated Bell's inequalities, confirming the underlying quantum weirdness that Schrödinger had labored to define. This did not directly vindicate his realist aspirations, but did validate his intuition that foundational questions mattered. By the late 20th century, technological advancements made the cat more than just a metaphor. Physicists learned how to create superpositions of increasingly larger systems, atoms, molecules, and tiny mechanical resonators, producing states that were cat-like in the sense that Schrödinger had feared. Two mutually exclusive realities coexisting until interaction or measurement force a resolution. In laboratories around the world, Schrödinger cats became a technical term, referring not to furry animals confined in boxes, but to superconducting circuits, trapped ions, and photons in cavities, systems engineered to sustain two macroscopic possibilities simultaneously. He had originally conceived the image as a warning against taking superposition too literally. Ironically, the image became a roadmap for exploring superposition more literally than ever before. This new experimental landscape also brought another Schrödinger theme into sharper focus: decoherence. Schrödinger had questioned why macroscopic objects appear to have definite properties. Decoherence theory, developed primarily from the 1970s onward, explained how entanglement with the environment rapidly destroys visible superpositions, making a system appear classical without the need to invoke a special collapse rule. Decoherence did not fully resolve the measurement problem. Schrödinger would have insisted that it still failed to explain why one particular outcome becomes real, but it did explain why we don't observe cats that are simultaneously half dead. In a sense, decoherence provided a partial response to Schrödinger's critique. It accepted the fundamental principles of quantum mechanics and demonstrated how classical experience emerges from them through entanglement with the environment. His question had evolved into a research program. Meanwhile, alternative interpretations of quantum mechanics, the kind that Schrödinger had hoped for, gained traction. Bohmian mechanics, revived by David Bohm and refined by later thinkers, offered a realist picture in which particles have definite positions guided by a wave. The many worlds interpretation, popularized by Hugh Everett's 1957 idea and later championed by others, asserted that there is no collapse at all. All possible outcomes occur in branching universes. Objective collapse models propose that collapse is a real physical process triggered by mass or complexity. Each of these interpretations represents a different attempt to address the same discomfort that Schrödinger had felt in Zurich and Berlin. None has achieved universal acceptance within the field. However, their very existence is proof that the theory's meaning remains an open and evolving landscape, not a settled conclusion. Schrödinger's lifelong resistance played a significant role in keeping that landscape open to exploration. His influence extended far beyond the realm of foundations. His wave equation remains the beating heart of quantum science. Every chemist solving molecular orbitals, every engineer designing semiconductors, and every physicist modeling atomic traps still relies on Schrödinger's formalism on a daily basis. It is difficult to find a modern technology that does not, in some way, depend on his mathematics. Lasers, MRI machines, transistors, quantum optics, and superconductors are not mere footnotes to his work. They are its direct descendants. Yet, Schrödinger's legacy is not solely functional. It is also tonal. He taught physicists to embrace imagination without allowing to become detached from rigorous thinking. His equation is beautiful, but so is the way he arrived at it, by insisting that a new theory must restore continuity and clarity in areas where classical thinking had broken down. Even his philosophical dissent carried a valuable lesson. A scientist can contribute to the development of a theory and still refuse to stop questioning its meaning. In an era where success often tempts people into complacency, Schrödinger's refusal to settle feels quietly courageous. His book Asterisk What is Life? Asterisk also continues to resonate. Molecular biology experienced explosive growth after his death. The discovery of DNA's double helix, the deciphering of the genetic code, and the understanding of the logic of replication became the new narrative of life. And many of the architects of that narrative acknowledged Schrödinger as an early inspiration. He had not predicted the double helix in its specific detail, but he had insisted that heredity must be understood in physical terms, as information carried by stable molecules. That insistence helped transform biology into an information science. In this sense, Schrödinger became a bridge not only within physics, but also between physics and living matter. There's another, more subtle aspect to his legacy, his way of thinking about unity. Late in life, he explored the idea that separateness might be less fundamental than we perceive it to be. Whether one agrees with this idea or not, quantum entanglement has made similar questions unavoidable. The world is indeed woven together more tightly than classical intuition would suggest. Schrödinger did not fully resolve the philosophical implications of this insight, but he sensed its significance early on. His mind was attuned to connections between waves and particles, between physics and biology, between nature and human understanding. So, what does a story feel like when viewed in retrospect? It feels like a river that divides and then merges again. On one bank stands a triumphant mathematician of 1926, who bestowed upon science a line of beauty so powerful that it continues to shape our understanding of reality. On the other bank stands a restless philosopher, who never ceased questioning the nature of reality itself. Between those banks flows a single life, simultaneously embodying both roles. Schrödinger's cat, in the end, is not a mere gimmick. It is a mirror reflecting the strange paradox at the heart of quantum mechanics, a theory that makes flawless predictions, yet compels us to reconsider what prediction itself even means. Schrödinger provided us with the mirror and then dedicated the rest of his life to gazing into it, not out of confusion, but out of intellectual honesty. When people today speak about quantum weirdness, they often sound delighted. Schrödinger, if he were listening, might offer a small, wry smile. He was undoubtedly delighted by the mathematics, but he was also troubled by the metaphysics. He would likely remind us that wonder is not the end of the intellectual journey. It is merely the beginning, and that a theory as successful as quantum mechanics deserves not only applause, but also the patience to grapple with the most challenging questions it raises. That ultimately is where his legacy resides, not in a single definitive conclusion, but in a continuing posture. The posture of someone who can simultaneously embrace beauty and doubt, and who continues to move forward even when the meaning of the path ahead remains uncertain.